Hello and welcome to another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler, and today we'll be doing Unit 6, Lesson number 7 on squares. One of the remarkable things about squares is that they are one of the first geometric objects you ever study, or even see, right? As early as literally when you are still in diapers, or at least when my kids were still in diapers, we were looking through books that had shapes in them, right? Circles, squares, triangles, and you'd always point at that thing and say, that's a square, right? The irony of the square is that although it seems like one of the most simple quadrilaterals, it is actually the most complex, meaning that it has the most special properties to it. And let's take a look at why. All right, squares. Any quadrilateral with 4 congruent sides and 4 right angles. 4 congruent sides and 4 right angles. Now right away, I want to kind of push you a little bit to then think about what other types of quadrilaterals squares are. All right, so let's take a look. Exercise number 1. Based on the definition above, a square is which of the following special quadrilaterals? Give a reason for why it is or isn't below each. All right, so what I'd like you to do is think about which of these 4 things a square also is. So is it also a rectangle? Is it also a rhombus? Is it also a parallelogram? Is it also a trapezoid? All right, and if it isn't, fine. But if it is, give a reason why. Okay, pause the video now and think about this a bit. All right, let's go through it. Well, is a square a rectangle? Yes. Yes. Why? Because it has 4 right angles, right? That's what makes a rectangle, is that it has 4 right angles. Since a square has 4 right angles, it is a rectangle. All right, is it a rhombus? Yes, because it has 4 congruent sides. Whoops, I don't know what happened there. It has 4 congruent sides. So a rhombus is any quadrilateral. Let me get rid of random red dot. Rhombus is any quadrilateral that has 4 sides of equal length. Since a square has 4 sides of equal length, it is a rhombus. Is it a parallelogram? Yes. Yes, and there's many explanations you can give for why it's a parallelogram, but maybe one of the easiest ones is let's go with the rhombuses. All rhombi are parallelograms. You could also say yes, because all rectangles are parallelograms. And finally, is it a trapezoid? And the answer is yes. Why? Well, that's because all parallelograms are trapezoids. By the way, as some of your teachers have probably pointed out to you, the idea that all parallelograms are also trapezoids is a new concept. All right? There are probably even some of you who are watching this video who live in states where perhaps they haven't swung over to that definition. It's what's called the inclusive definition of a trapezoid, okay? The inclusive definition of a trapezoid says that a trapezoid has to have at least 1 pair of parallel sides, meaning that it could have 1 pair or 2 pairs, as a parallelogram does. Other states go with what's called the exclusive definition of a trapezoid, stating that a trapezoid has exactly 1 pair of parallel sides, and therefore no parallelograms are trapezoids. In the Common Core, generally speaking, we go with the inclusive definition, which says that all parallelograms are also trapezoids. But again, you should talk to your teacher and find out which way your particular state looks at it, and also how they test it, because that's pretty important too. All right, let's keep going. Oh, actually, let's go back to one last thing on the screen, right? Because this is what it's all about, right? A rhombus plus a rectangle gets you a square. Now, the reason that that's important is that rhombuses had a lot of properties to them, and we saw those in the last lesson. Properties like the diagonals bisecting the angles, the diagonals being perpendicular to each other. The square gets those properties as well because it's a rhombus. Remember, rectangles, they have a nice property, and that's the fact that the diagonals are the same length, right? That's the big one with rectangles, is that the diagonals are the same length. And again, squares get that as well because all squares are rectangles. So squares get all of this stuff that both rhombi and rectangles have. All right, and we're going to use those in problems today. All right, so let's jump right into a design problem using squares. Squares come up a ton in the real world, and so we have to be prepared to use their properties to be able to answer various questions. This one's a little bit wordy. Let's go through it together. Exercise 2. Kimmy is designing a square garden whose diagonal is exactly 16 feet long. She would like to place fencing around the perimeter of the garden so that it is completely surrounded. If the fencing she likes comes in 12-foot long rolls, how many rolls will she need, and how much fencing will be left over when she's done? Show all calculations that lead to your final answers. All right, so this is kind of cool, right? And obviously it's helpful if we draw a good picture, okay? What I'd like to do though, you know all the math that you need to do this problem, all right? It's kind of lengthy. What I'd like you to do is pause the video now and take a shot at it, and then we'll work through it. All right, let's do it. Good picture. Let's start with that. Now notice it says that its diagonal is 16 feet. It doesn't have to say it's shorter diagonal, it's longer diagonal, because the plain fact is, due to the fact that it's a square, and squares are rectangles, the two diagonals are the same length. So what do I know about this square? All I know is that this is 16 feet long, and yet I want to put fencing around the square, so I need to know what its perimeter is, okay? Now what that means is I need to know what a side length is. Maybe I'll call it x. But of course, because a square is also a rhombus, all side lengths are the same, and because a square is a rectangle, all of these angles are 90 degrees. So what I'm now dealing with is I'm now dealing with an isosceles right triangle that kind of looks like this. And because it's a right triangle, I can now use the Pythagorean theorem to figure out how long the side length is. Now, generally speaking, in the Pythagorean theorem, you can only use that if you know two of the side lengths and you're missing the third one, whichever one it is, the A, the B, or the C. In this case, because the two sides that are missing are the same length, we can use the Pythagorean theorem. Now obviously, the Pythagorean theorem is a squared plus b squared equals c squared, but in this case, I'm going to have x squared plus x squared is equal to 16 squared. That's going to be x squared, 2x squared. Be careful there. And of course, 16 squared we can do on our calculator if we don't have it memorized, 256. Now be careful, of course, this isn't a course in algebra, but you need to know things that like x squared plus x squared is 2x squared. It's not x to the fourth or anything like that, right? And now we need to solve for x. So we're going to divide both sides by 2. All right, and that's going to give us 128. X squared is 128. And now we need to solve for x, so we're going to take the square root of both sides. Now 128 is not a perfect square. It's kind of an ugly number, so we're going to have to go over to our calculator right now. That's no big deal. I just got to get out of this mode and go over to here, our nice TI graphing calculator. What was I doing? Well, I had my 256 and I had divided it by 2, right, to get my 128. And now I have to take the square root of that. I could have just done square root of answer or whatever. So the actual side length of my square is a little bit messy. It's 11.313, etc. feet, right? Remember, that's the side length of a square. I'll go with 11.31 for right now. Let me just pop back into here really quick. And I'll just put 11.31. Now, I need to have the entire perimeter. I need to go back to my calculator for that really quick. But one of the beautiful things all I have to do is take this and multiply it by 4, right? Answer times 4. And now this is my perimeter. My perimeter is 45.25, 45 and a quarter feet. All right, so the perimeter, we'll just use a big P for that, 4x, is 45.25 feet. Now remember, the question was or the question asked us, how many rolls of fencing would we need if, right, the rolls came in 12-foot sections? Now, for many of you, the numbers are small enough here that you could actually kind of just work this out for yourself. But, of course, if I needed to, I could just take that answer and divide by 12. I need to know how many 12-foot rolls I need to buy. And all things perfect, I would need to buy 3.77, etc. rolls of this fencing. I can't do that. Stores don't allow me to do that, generally speaking. So I'm going to have to buy 4 rolls, right? I'm going to have to kind of round up no matter what. I'm going to have to buy four rolls of fencing. And of course, four rolls of fencing at 12 feet per roll is 48 feet of fencing. Okay, so let's go back over here. I'm going to go into View, Full Screen. So I'm going to need 4 rolls of fencing. That's part of my answer. All right, that's how many I'm going to have to buy. Hello, magic red dot. 4 rolls of fencing. It also asks me how much fencing will be left over when she's done. Well, the 4 rolls of fencing give me 48 feet, right? But I only needed 45.25 feet. So that's actually, when I subtract, is going to leave me with 2.75 feet left over. So almost 3 feet of fencing left over. Not too bad. It would have been a shame had we needed, let's say, 37 feet of fencing, right? And then we could have gotten 36 feet with 3 rolls, but we would have had to buy 4 rolls, and then we would have had a lot of waste. Here, we're just wasting 2.75 feet of fencing, right? We need the 4 rolls to get us above that 45.25. That gets us the 48 feet of fencing, and then we have 2.75 left over. All right, let me step out of the way so you can take a look at this. Remember, a lot of this we did on the TI calculator. All right. Okay, let's move on. Let's keep going. Let's see what else we have. All right, exercise number 3. Okay, now we're going to get back a little bit into reasoning and proof land, although I think I'm going to stick with kind of a paragraph proof on this. Let's take a look at a kind of a neat problem involving the reasoning with squares. Exercise number 3. In the diagram to the right, square ABCD is drawn, and the midpoints of its sides have been marked and connected with segments to form quadrilateral EFGH. Give an explanation for why EFGH must also be a square. Now again, it probably seems rather obvious that if I take this larger square, ABCD, and I mark off its midpoints, E, F, G, and H, and then I connect them, oh yeah, of course, that's a square. It's obvious it's a square, all right? But why? This is actually rather complex given how much it takes to be a square. So what I'd like you to do is pause for a moment and think about how you would go justifying that this inner figure, EFGH, is also a square. And it's a little bit of a challenge, okay? And we'll go through it. Yeah? Let's go through it. Again, that little pause I gave, that's not the amount of time it should have taken you to think about it. That's the amount of time it should have taken you to pause and then unpause the video, okay? You may have taken quite a bit to think about this. So let's talk about what we know. All right, what I know definitely is I know all of these angles are right angles, right? Now, I also know that all 4 sides of the larger square, the larger quadrilateral, are congruent. And then, because of those midpoints, I also know that this is congruent to this, but of course that means this must be congruent to this, and this must be congruent to this, and this must be congruent to this, etc. All right, I didn't get my right angle here. Let's get that one in. And so what can I do with all of that? Well, I can say that these 4 right triangles, right, AEH, BFE, etc., right, I can say triangle AEH is congruent to triangle BFE, which is congruent to triangle CGF, which is congruent to triangle DGH, by side, angle, side. So those four right triangles are identical to each other by side, angle, side. Okay? Now, what does that get me, though? What that gets me, then, is the fact that EH, EF, FG, and GH, right, those four sides, HE, must be congruent to EF, must be congruent to FG, must be congruent to GH, right? And that's by CPCTC, right? If you will, they are the hypotenuses of those four congruent right triangles, and since they're all hypotenuses, they are corresponding parts of congruent triangles, so they must be congruent themselves. And of course, this is very important, because there's two things that make a square a square. Number one, all four sides are the same length. And we just established that. That is the same as that, is the same as that, is the same as that. But the other piece is somehow, we need to justify, I'm going to do it in red, we need to justify that those four angles are right angles. Now, we haven't done that yet. And that's a little bit trickier. That's a little bit trickier, okay? But let's re-examine maybe one of these little right triangles, right? So if we're thinking about triangle AEH, go back to blue, right? If we're looking at triangle AEH, then this thing is an isosceles right triangle, an isosceles right triangle, which means these two angles have to be the same measure, right? The base angles of an isosceles triangle are congruent. And what do they both have to be? Think about that for a minute. Well, these two angles, right, along with that 90-degree angle, must add up to 180. And because of that, these two angles must add up to 90. And of course, 90 divided by 2 gives me each one of those angles being 45. Right, so that's a 45-degree angle, that's a 45-degree angle, and then I can go on and say all of those must be 45-degree angles, because these are, after all, congruent right triangles. Whoops. 45, 45, 45, and 45, right? All of those have to be 45-degree angles. But, right, the final little piece, one more time, let's go in maybe green this time. These three angles must sum to be 180 degrees, as well as these three angles and these three angles, etc. Well, I've got a 45 and I've got a 45. If I add those together, I get 90. Since all three of them must add up to be 180, right? I now can do 180 minus 90, and that, of course, is another 90-degree angle. And that is what gives me the 4 90s, right? So I can establish, this isn't exactly a proof, but I can establish using facts that I know about isosceles triangles, isosceles right triangles, and the rest of it, I can now use to establish not only that that inner figure, that inner quadrilateral has 4 congruent sides, that's by CPCTC, but also that the 4 angles are 90 degrees. All right? Let's keep going. Exercise number 4. Okay, back to the coordinate grid. Quadrilateral ABCD has coordinates of -4, 2, 4, 8, 10, 0, 2, -6. Using coordinate geometry, prove ABCD is a square by showing that it has 4 sides of equal length and 4 pairs of perpendicular sides. All right, let's do it. Now, there's many different ways to prove something is a square in the coordinate grid, and that's because there's many ways to prove that something is a parallelogram, to prove something is a rectangle. A rhombus is pretty straightforward, but there are different ways to do that. When I'm trying to prove, though, that a figure is a square in the coordinate plane, I pretty much go brute force, which means I want to show that all 4 sides have the same length and that I've got 4 pairs of perpendicular sides, in other words, 4 right angles. So let's first talk about how we determine that all 4 sides have the same length. Well, which tool would we use from coordinate geometry to do that? We're going to use the distance formula. So let's take a look, all right? Let's go through, not AD, let's go through AB, okay? Let's find the length of side AB using the distance formula, right? And remember, the distance formula says we're going to take x2 minus x1, 4 minus negative 4, square that. It's the Pythagorean theorem, right? Then we're going to do 8 minus 2 squared. 4 minus negative 4 is 8 squared. And then I've got 6 squared. Add those two together, I get the square root of 100, and that's 10. All right? Now what I'd like you to do is use the distance formula to find the lengths of sides BC, CD, and DA, or AD, however you want to look at it. And hopefully each one of them will also turn out to be 10 units. But why don't you pause the video now and take a little bit of time to do that. All right, let's go through them. And of course they do all end up being that 10 units, but we should verify it. Let's go through BC. The distance formula there, we're going to have 10 minus 4 squared plus 0 minus 8 squared. That's going to give me the square root of 6 squared plus negative 8 squared. Again, the square root of 100, and that's 10. Let's do CD now. The distance formula there. All right, we've got 2 minus 10 squared, negative 6 minus 0 squared. Lots of squaring here. Negative 8 squared plus negative 6 squared, again giving me the square root of 100, which is 10. And finally, DA. And what would we have there? We'd have 2 minus negative 4 squared plus negative 6 minus 2 squared. Whew. That's going to be 6 squared, although that doesn't really look like a 6, so let's see if we can make it look a little bit better. Yeah, that looks great. 6 squared, negative 8 squared. Look at all these 6s and 8s coming out in this problem. All right. Now, what we've really done, of course, in this part of the proof is we've shown that ABCD is a rhombus. Right? That's what we've done. We've shown it's a rhombus. Now what I need to do is also show that it's a rectangle. Now again, there's different ways to do that. One way to do it is to actually just calculate the lengths of the two diagonals. And if they're the same length, you're actually done. It's then a rectangle and a rhombus, which means it's a square. What I'm going to do though is I'm just going to establish the fact that there are 4 pairs of perpendicular sides. So let's go through that. And we do that, remember, by using slope. Okay? So I'm going to find the slope of all 4 sides, or maybe I'll find the slope of side AB first, then have you work on the others. All right, so for AB, its slope, remember, will be y2 minus y1, all right, divided by x2 minus x1. All right, that's going to be 6 divided by 8, and that's a slope of 3/4. All right, so there's my slope for AB. Why don't you go ahead and calculate the slopes of BC, CD, and DA, and then try to make some statements about perpendicularity based on those slopes. Take a minute. All right, let's go through it. All right, so we have AB. It's got that slope of 3/4. Maybe I'll kind of put my BC in here. Let's see if I can squeeze that in. BC has a slope of 0 minus 8 divided by 10 minus 4. Be careful with your signs. That's going to be negative 8/6, and that will reduce to negative 4/3. Now, before we even move on, though, notice, right, I got a slope of 3/4. I have a slope of negative 4/3. Those are called negative reciprocals, right? And because they have negative reciprocal slopes, that means that AB and BC must be perpendicular to each other. What that immediately does is gives us that right angle. All right, let's keep going. We have 2 more slopes to calculate. Let's calculate the slope now of CD. All right. The slope of CD is going to be -6. Whoops, wow, that was one very red 6. -6 minus 0 divided by 2 minus 10. Be careful here. We're going to get -6 in the numerator and -8 in the denominator, and a negative divided by a negative is a positive. Specifically, here, a positive 3/4. Now, the fact that these two are both 3/4 means that those two sides are parallel to each other. Not a surprise, given that a square must be a parallelogram, but we're not really too interested in that. Let's do one last one. Let's find the slope of DA. All right. Specifically, let's see, the slope of DA will be -6 minus 2 in the numerator, and 2 minus -4 in the denominator. Again, be careful with your signed numbers here. That's going to be a -8 in the numerator, a positive 6 in the denominator, which is going to reduce to -4/3. Again, not surprising that we've got a -4/3 and another -4/3 given the fact that it's a parallelogram. But again, not really the point. What I want to now say based on those slopes, and let me kind of move this out of here, is that AB is perpendicular to BC, okay, comma, BC is perpendicular to CD, comma, CD is perpendicular to DA, comma, and DA is perpendicular to AB. All right, notice how I have to do that because each one of these statements is establishing the fact that I have a right angle. And you want to give a little reason here where you can say, because slopes are negative, I'll just abbreviate this, negative reciprocals. So let's wrap it now. Let's make a final statement. A, B, C, D is a square because it has 4 congruent sides and 4 pairs of perpendicular sides. And you could also say that it's got 4 right angles. 4 pairs of perpendicular sides. Almost looks like the word perpendicular. Right? Now again, there are definitely other ways of proving something is a square in the coordinate grid, but to me this is the most straightforward. We established that all 4 sides are the same length using the distance formula. Then using the slope formula, we established the fact that we've got 4 pairs of perpendicular sides, or 4 right angles, however you want to think about it, and therefore we have a square. All right. Let's go on and do one final exercise. See, because what the last one gets at is that there are definitely many, many different ways to prove something is a square. What I want to know is whether or not particular scenarios give us enough information to conclude that a quadrilateral is a square. So let's take a look at that in the last exercise we're going to do. Exercise number 5. For each of the following sets of conditions, carefully explain why they are enough to show that a quadrilateral is a square. Why they are enough to show a quadrilateral is a square. Think about each piece of each condition and what it tells you. Okay, so in each one of these situations, we're given enough information to conclude it's a square. But why? Okay, so let's do the first one together and then have you think about the other 3 on your own. Letter A quadrilateral with 4 equal sides and 1 right angle. Right? Why is that? Why would that be enough to know that it's a square? All right, well, let's talk about it. Right? It's enough to know it's a square because 4 equal sides makes it a rhombus. And thus a parallelogram. Okay, so the fact that it's got 4 equal sides means it's a rhombus, and the fact that it's a rhombus means it's a parallelogram. But any parallelogram with one right angle must be a rectangle. All right? And anytime we have a quadrilateral that is both a rhombus and a rectangle, it is a square. All right? So that's it. You take a look at the other three scenarios and see if you can explain why it gives us enough information to know it's a square. All right, let's go through them. Letter B, a parallelogram, so we're starting off by knowing it's a parallelogram, with equal diagonals and two adjacent sides of equal length. All right, so this is enough. If I tell you you have a parallelogram that has equal diagonals and two adjacent sides, adjacent means touching sides, of equal length, then I know I have a square. So why is that? Well, apparently I'm going to have to write a lot smaller here. But a parallelogram, maybe abbreviate, a parallelogram with equal diagonals is a rectangle. All right? And we proved that a while ago. Anytime you have a parallelogram, it's got to be a parallelogram. Anytime you have a parallelogram whose diagonals are the same length, then it is a rectangle. Okay? Now can we get the rhombus part of it? Okay? So, any parallelogram that has two adjacent sides equal must be a rhombus. All right? That may need actually some additional explaining, but if you think about it right, in a parallelogram, opposite sides are always the same length. So therefore, if we had a parallelogram that had two sides that were touching in the same length, well then all four sides would also have to be the same length, and therefore it would have to be a rhombus. Okay? Let's take a look at letter C. A parallelogram with perpendicular equal diagonals. Awesome. A parallelogram with perpendicular equal diagonals. Well, this one's really great. If a parallelogram has perpendicular diagonals, it is a rhombus. A rhombus. If a parallelogram has equal diagonals, it is a rectangle. Okay. And again, that's the key. Notice in each one of these, we come back to the fact that it's a rectangle for this reason, it's a rhombus for that reason. Put a rectangle and a rhombus together, and you have a square. All right, last one, letter D. A quadrilateral whose diagonals are perpendicular bisectors of one another, quadrilateral whose diagonals are perpendicular bisectors of one another, and one right angle. Okay? And this one requires a little bit more work, all right? Because we're not starting with a parallelogram, we're starting just with a generic quadrilateral. Okay? So it kind of goes like this. If the diagonals of a quadrilateral bisect each other, it is a parallelogram. All right, so the first thing that we know or the first thing we can get, is the fact that the diagonals are perpendicular bisectors, not so much the perpendicular, but the bisector, right? If they're perpendicular bisectors, just bisectors, then it's got to be a parallelogram. Since they are also perpendicular, it is a rhombus. All right? But, whoops, since it is a, give myself a little bit more room, since it is a parallelogram, with a right angle, it is also a rectangle.